Volcano tectonics is a scientific field that uses the techniques and methods of structural geology, tectonics, and physics to analyze and interpret physical processes and the associated deformation in volcanic areas, at any scale. These processes may be 1. Magma-induced or, conversely, 2. Control magma propagation and emplacement. In the first case, the process has a local extent, usually within the volcanic area. Typical examples include the development of calderas and resurgences, pit craters, dikes, sills, laccoliths, magma chambers, eruptive fissures, volcanic rift zones and any type of volcano flank dynamics, including sector collapses. In the second case, the process controlling the magma may have a regional extent, also outside the volcanic area. Typical examples include the activity of regional faults and earthquakes along divergent, convergent, and transform plate boundaries, as continental, transitional and oceanic rifts, magmatic arcs, and back arcs, as well as of any intraplate structure possibly controlling volcanism. In fact, an increasing number of studies has been considering also the volcano-tectonic features of extraterrestrial bodies, including Venus, Mars, and Jupiter's moon Io. As a volcano consists, in the broadest sense, of a volcanic edifice, a plumbing system and a deeper magma reservoir, volcano-tectonics is not restricted to the surface processes, but also includes any subsurface process in the host rock related to the shallower and deeper plumbing system of the volcano. The latter may be directly accessible in the eroded portions of active volcanoes or, more commonly, in extinct eroded volcanoes. The general aim of volcano tectonics is to capture the shallower and deeper structure of volcanoes, establishing the overall stress-strain relationships between the magma and the host rock, to ultimately understand how volcanoes work in their regional context. This approach allows defining the dynamic behavior of active volcanoes during unrest periods and eruptions and thus being able to make reliable forecasts as to the likely scenarios. Volcano tectonics merges the knowledge and expertise of a wide range of methodologies. These primarily include structural geology, usually at the outcrop scale, tectonics, usually at the regional scale, geodesy from active volcanoes, GPS, in SAR, leveling, strain meters, tilt meters, geophysics, seismicity, gravity, seismic lines, remote sensing, optical and thermal, and modeling, analytical, numerical, and analog models. More volcanological-oriented methodologies are also involved, including stratigraphy, petrology, geochemistry and geochronology. Data, however, are of little use if they cannot be interpreted and understood within the framework of a reasonable model or theory of volcano behavior. Quantitative and testable models must, in the end, be related to some physical theories and thus to physics. In volcano tectonics, like in solid earth geophysics in general, the main physical theories used are those that derive from continuum mechanics. For solid earth sciences, these are mainly solid mechanics, including rock mechanics, fracture mechanics, and general tectonophysics, and fluid mechanics, including fluid transport in rock fractures.